Hello, my name is Anastasia Guenova and I'm a 10th grade student in Sofia, Bulgaria. Today, I'm going to tell you more about ferrofluids and magnetic hills. For the record, this is the official name of the topic. Okay, so let's take a look at the agenda for today. First of all, we are going to look into the origins of ferrofluid. Then, we're going to talk about the synthesis of ferrofluid and how it's made. After that, I'm going to tell you how you can make your own ferrofluid at home. Then, we are going to add some color to the mixture to get some sparkle. And finally, we are going to make some experiments with ferrofluid and examine how they behave in various conditions. A ferrofluid is a liquid that becomes strongly magnetized in the presence of a magnetic field. Ferrofluids were first invented in 1963 by NASA's Steve Papel as a rocket fuel. A ferrofluid is a collection of superparamagnetic nanoparticles that are suspended in a liquid. These nanoparticles are approximately 10 nanometers in diameter, and the majority of them, like the ones we are using, are iron-based. If as synthesized nanoparticles are put into a solution, they aggregate and form clusters. This is called the van der Waals interactions. These clusters are too large to be kept in suspension by Brownian motion and settle to the bottom of the container. The use of a magnet can accelerate the settling of these clusters, allowing for easy washing of the particles. Okay, so here are the main steps of synthesizing a ferrofluid. Ferrofluids respond to an external magnetic field, enabling the solution's location to be controlled through the application of a magnetic field. Iron oxide magnetite nanoparticles can be produced by mixing two oxidation forms of iron salts together in a basic solution. These particles must remain small and separated from one another in order to remain suspended in the liquid medium. Surfactants are used to prevent nanoparticles from approaching one another too closely. Once prepared, ferrofluids have the captivating property of exhibiting spikes when placed in the proximity of a strong magnet. Normally, to make a ferrofluid, you need some equipment and materials that can be hard to get. So instead, I'm going to show you how to make your own ferrofluid at home. So here's what you need: a bar magnet, some iron fillings, a shallow dish, some vegetable oil, and a sponge or a napkin. I made this at home and it was very easy. Also, my mom didn't get too angry at me, which, to be honest, is the most important thing. Even though it's relatively simple, it's still important to stay safe. I recommend you wear work clothes and safety goggles if possible. So here are the main steps of making a ferrofluid at home. First, pour a bit of vegetable oil into a shallow dish, just enough to make a thin film across the bottom. Second step, pour iron fillings into the oil and mix the two until they have become a thick, sludge-like material. And step 3, use a napkin or sponge to absorb any excess oil and allow the ferrofluid to become thicker. A good way to do this is to attach a magnet to the outside of the dish. This will solidify the fluid and let you dab away extra oil. You are done. Now you can play with it and investigate. But please be careful, because the stains that a ferrofluid causes are very hard to get out. Okay, so now that we have our ferrofluid, let's give it some color and see what happens. I found several different ways to color a ferrofluid online. I choose to make my ferrofluid glow in the dark because it's really beautiful, just like science. Follow the next steps to make your own glow in the dark ferrofluid. Step 1. Get a glow stick and break it so that it starts glowing. Second step. Extract the luminescent liquid into a petri dish. Step 3. Mix the luminescent liquid with the ferrofluid. Use a magnet to stir well. And step 4. Turn off the lights and enjoy the view. What I observed after 20 minutes of playing with the colored ferrofluid is that the liquid stopped being responsive to the magnet. Most likely there is a chemical reaction which oxidizes the ferrofluid, so it changes its chemical composition. I have to do some more experiments to be sure exactly what's going on. So here are some observations I made during the experiments. The ferrofluids are a vast subject and experiments to discover new qualities in them are carried out to this day. It is still an open subject and there are some findings with formidable complexity. Using 2.5 milliliters of ferrofluid and a neodymium magnet with the power of 203 newtons, and after a lot of counting, I made the following observations on the number of spikes as a function of the distance of the ferrofluid from the magnet. I observed that the factors which will affect the distance at which spikes formed are the strength of the magnet, the magnetic strength of the fluid, and the orientation of the magnet as it approaches the dish. When I pulled the magnet away, the spikes disappeared, because individual particles of magnetite behave as tiny magnetic domains. Therefore, in the absence of a magnetic field, and as a result of thermal agitation, the particles' magnetic domains become randomly orientated relative to one another and the spikes disappear. The obvious next question is why the magnetic spikes don't stick together. That's because in ferrofluids there must be something that acts as a dispersing agent or surfactant. This agent must adhere to the particles, surround them completely, and create a net repulsion between them. This means they can't stick together. The patterns retained a circular symmetry right up until the magnet pressed to the petri dish. When I put a metal coin in the petri dish, I observed some interesting structures. As I brought the magnet closer to the ferrofluid, the coin stands on its side and the ferrofluid climbs on the top of it. You can try to do this at home as well, but please be very careful because you can have a lot of cleaning to do. Thank you for your attention. If you have any questions, please don't be shy to email me over here. I would like to see you soon.